Good morning, everyone. So I'm going to be talking about work done in Julien Michel's group with a PhD student, Antonia Mey, and our collaborator in biology, Malcolm Wilkinson, on looking at catalytic activity in cyclophilin. Okay, this does not work. All right. So particularly the Michel group is interested in actually exploiting cyclophilin as a drug target. And we're kind of working on this in different avenues. Why are we doing this? Cyclophilin is an interesting drug target because particular its functionality in what viruses can do with it. It can viruses will hijack cyclophilin and use it in the virus capsids. So if we can stop that from happening, that's great. Cyclophilin is also an enzyme and actually catalyzes the cis-trans isomerization of proline. And there is an available drug out there, cyclosporin, but the problem with it is that actually there are 17 different isoforms of cyclophilin, and cyclosporin is not isoform selective. So what we're particularly interested in is trying to specifically target cyclophilin A by trying to explore loop motions of this hundreds and 70s loop. And this is not what I'm talking about, but because of work we've been doing here, this entire project I'm talking about kind of came out of it. And therefore, I'm actually going to do a little excursion into what is sort of experimentally out there on cyclophilin A. So there's a bunch of NMR measurements that date back to the early 2000s, done by Eisenmesser and al., where they basically managed to distinguish two groups of motions in cyclophilin, which are slow motions and slower motions. And in particular, there's a bunch of residues that belong to a group 1 and another bunch of residues that belong to a group 2 that exchange at hundreds per second to thousands per second rates and slightly faster motion. And these group 2 motions are actually what Jordi's going to talk about in his next talk and what kind of prompted this work here. And in fact, we're kind of looking at the group 1 motion without really trying to achieve these timescales. But essentially what the experimentalists hypothesized that this millisecond motion of this major to minor conformation involving these group 1 residues occurs at the same time as catalysis. So they might be related. In order to test this, they looked at crystal structures, and what they found is that this phenylalanine 113 actually takes two rotameric state, the plus 60 and minus 60 rotameric state, and they thought, well, if we design a mutant that kind of pushes this rotameric state to phenylalanine in this minus 60 conformation, what will happen to the catalysis? So they designed this S2T mutant, and indeed, what they observed is that it only occupies this minus 60 rotameric state. And it's quite interesting, this mutation is actually a allosteric site because it is quite far away from the catalytic arginine 55. So then they actually measured the effect of this mutation, and indeed, there was a 60-fold reduction in the speed of process 1 motion, so these residue 1s, group 1 residues, and a 70-fold reduction in catalytic activity. And then earlier this year, another paper was published in Nature Communications by Otten and al., where they designed a further set of mutants that partially actually recover this catalytic activity. So the reason why we got interested in actually trying to assess this catalytic activity is because in Jordi's simulations we saw a lot of movement of this phenylalanine 113. So we wanted to investigate that a bit further. So we started by looking at the apoprotein and just generated 200 nanoseconds data for the 4 mutants, and then we did a very simple MSM analysis of looking basically at a bunch of side chains. But before we even go into the MSM analysis, what we see is a lot of transition of this phenylalanine here. So this is a single trajectory trace, and yes, it flips up and down quite a lot. But what happens if we look at the mutant? That also happens. And the same story for all the other mutants. Obviously, it's quite nice. We can just look at this trajectory trace, but wouldn't it not be better if we could quantify this a little bit numerically, as in how fast these transitions occur? So we built a Markov state model. And obviously, the nice thing about a Markov state model, it gives you information about stationary probabilities, but also kinetics. So first of all, we looked at the populations of these two rotameric states as weighted by the Markov state model, so that we have the -60 state and the +60 state, and compared that to the X-ray occupancy found in the experimental data. And the Markov model was sort of constructed on a set of side chains that mainly belong to these group 1 residues. So we recover the crystal occupancy quite well with our simulations, and this is sort of the dynamic information we get. Here I'm only showing wild type and this S99T mutant, and we see exchanges between these states that are much faster as what the NMR measurements suggest. And it's also because obviously we're looking at a timescale that is much faster. Our simulations are not long enough to actually look at these long timescales. But basically the point here is that even the short simulations do see this exchange. So then we wanted to see how that would potentially relate to catalytic activity. So we designed an umbrella sampling study where we took this peptide AAPF with this proline residue here and biased this omega angle in order to see how the catalysis works, essentially. Here's some simulation information, and we did a WAM analysis for the umbrella sampling. And the nice thing, what we try to do is like, okay, we start in this +60 degree rotameric conformation of this phenylalanine and put the substrate in there and then run the umbrella sampling simulation. And then we get a nice improved catalysis over the AAPF in solution. However, if we do the same thing and kind of force this Chi1 of phenylalanine 113 into this -60 conformation, actually we don't get any improved catalysis at all. So what is actually going on? Why is this +60 state so much better? Well, there's some electrostatic stabilization. So we're now zooming in at the transition state region, and we get a massive stabilization through arginine 55, methionine, glutamine, and tryptophan. Whereas if we do look at the same things in the -60 simulations, the stabilization is gone. We can also further look at hydrogen bonding networks. So again, transition states of these two different simulations, in this case, again, looking at wild type and this one mutant, we have 6 hydrogen bonds with high probability in this transition state if we look at these simulations, whereas this is completely broken in the -60 degree state simulations. So this kind of leads us to proposing a slightly different model for catalysis than done by the experimentalists. So basically, they look at isomerization. So these rates for the wild type and the mutant, they can define a ratio between them. And this is sort of what the experimental paper of 2009 suggests. Using our MSM data for the populations of the states and transition state theory from umbrella sampling, we can kind of massage our data in a very simplistic way to actually match this ratio of rates. And we believe the reason how the catalysis works is actually because the substrate cannot bind well to this -60 conformation. So as long as there's a fast interchange between these two states, the catalysis will occur along this plus 60 F113 state in the wild type. But the same story will also be true for the mutant, but now this minus 60 state is a lot more populated, so we have to wait a lot more time to actually see conformations that are in this plus 60 state, and therefore we have a reduced rate in catalysis. So obviously it would be quite nice to test this experimentally. And also, again, we're actually not trying to necessarily, so there are two things actually. So what we observe with our simulations are fast local motions in the nanosecond to microsecond timescales. And in fact, the motions of this can account for the catalytic effect. At the same time, there may well be these slow global motions, but we're not actually trying to capture these in our simulations, in these types of simulations. And actually, Jordi is going to talk about these kind of motions in a bit more detail in a second. But so kind of putting this in an NMR type of perspective, sort of we're sitting in this regime here, which we can easily access with MD, and there should be some residual dipolar coupling experiments that might be able to be done in order to actually capture the side chain motion for this protein. Thank you very much.
Can you take a question or two, and then we can move to Jordi?
No.
I was wondering why you switched between force fields.
So basically, there was a paper published which had optimized torsion angles for these omega torsion angles, which showed that it experimentally recovers the activation barrier for the catalysis quite well. So we ended up using that for the umbrella sampling just because that was available in the literature. And then another study looking at the apoprotein used these CHARM22 data. So again, it was a matter of trying to be comparable what is out there. But yes, it would be quite good to also run. So there's a paper from 2009 as well, I think, where they have pretty much done the umbrella sampling of the wild type and compared it to experiments with a sort of optimized omega angle amber force field, and that's why we ended up using that.
Let's thank Antonia again.